Okay, so we're going to spend the next, well, so far we've actually been looking at networks of the kind that you have at the top, which are strictly feed-forward networks. When some information goes into the network, it gets processed sequentially from beginning to end. And after any neuron has actually processed a specific input, that neuron doesn't ever revisit that input. Even in your recurrent networks, a recurrent network was essentially just once unrolled. It was just a feed-forward network. So today and in the next two classes, we are going to go over a slightly different form of network, things with loops. So observe what's happening over here. You have some output coming out of a neuron, but then that's going back in to other neurons. So the output of any particular neuron depends on what has been output by the other neurons at the same time, which actually ends up requiring loopy operations. I was originally planning to talk about variational autoencoders today. I've changed the schedule a little bit because I want to introduce over the next three classes the notion that neural networks can be used to model distributions. Although in this specific format, the kind of distributions we will model are very different from what a variational autoencoder does. And then we will cover VAEs subsequently. Anyway, so consider this loopy network. This is the kind of network we've never seen before, at least in this class. So you have in this example a network of 5 neurons. The output of every neuron goes to every other neuron. And I'm going to assume for now that the neurons themselves are the old threshold activation neurons that we saw earlier, which means to say that each neuron operates on a weighted combination, an affine combination of inputs that comes in. And if that affine combination exceeds a threshold, the neuron is going to fire, otherwise it doesn't. The output of the neuron is +1 if it does fire, and it's -1 if it doesn't fire. So I'm going to use the +1, -1 notation. Now, we're going to simplify this network a little bit. Now, observe that every neuron has a connection. Every neuron I connects to neuron J, and at the same time, neuron J connects back to neuron I, and these two connections have different weights, right? So I'll simplify this, and I will consider a network where the connections are bidirectional. So the connection from neuron I to neuron J has the same weight as the connection from neuron J to neuron I. So what this means is that if I actually write this, the weights matrix for this network as if I arrange the weights of this network as a matrix, then the weights matrix is symmetric. Furthermore, no neuron has any connection from itself to itself, which means that the diagonal entries of this weights matrix are all 0. Right? So how is this kind of network is what is called a Hopfield net, where you have loopy connections. Neurons output information to them, to other neurons. Effectively, the output of any neuron at any time affects the output of that neuron at that time, or rather in response to any particular input. Because if there's an input, the neuron produces some output. That output is going to go to other neurons whose outputs will change, which is going to affect the input to the current neuron whose output changes, and so on. So there's a loopy there's a loopy transmission of information. So here's how you can sort of view the neurons, right? At each time, you can think of the neuron as receiving an incoming field. So every one of the neurons has some value, which is either +1 or -1. It has some weight with which it connects to every other neuron. And of course, every neuron also has a bias. So there's an incoming affine combination of the outputs of other neurons. We can think of this as some kind of a field. And the neuron is going to respond to this field. Now, if the affine combination is positive, the neuron is going to output a positive value, +1. If the affine combination is negative, the neuron is going to output a -1. So you can think of this differently. If the neuron is currently a -1, and the affine combination is positive, the neuron is going to switch from -1 to +1. If the neuron is currently a -1 and the affine combination is negative, it will not switch. So also if the neuron is currently a +1 and the affine combination is negative, the neuron is going to switch to -1 because you're basically the neuron output of the neuron is taking on the same sign as the affine combination, as the field itself. But if the field and the sign of the field and the sign of the neuron are the same, the neuron does not switch. So overall, you can think of the operation like so. If the sign of the field matches the sign of the current output of the neuron doesn't do anything. But if the sign is different, it's going to flip. Right? So you can think of it slightly differently. You can that if the field, if the product of the sign of the field, if the field and the current output have the same sign, then the product is positive. If the field and the current output have different signs, then the product is negative. So alternately, you can say that if the product of the current output of the neuron and the field of the neuron is negative, the neuron is going to flip itself, otherwise it doesn't flip itself. Everybody with me? Right? So it's a very straightforward and simple concept. And so the neuron flips if the weighted sum of other neuron outputs is of the opposite sign as itself. In other words, if the field that it currently receives is of the opposite sign of itself. But then here's the problem. When the neuron receives a weighted, let's say the current field of the neuron is of a different sign than its current output, then the neuron is going to flip. But when the neuron flips, what happens? It changes the field at other neurons. So those neurons in turn might flip. But if those neurons flip, that changes the field of the current neuron, which means the neuron might flip yet again. And this process could continue. Right? So here's the kind of, I've been trying to fix this figure for years, but I think it remains bogus. Nevertheless, I'll try to convey the idea. So here I have only positive and negative edges. Now you'll notice there's a cunning line with which is both red and blue. I'll change the sign depending on what I want it to do. But anyway, this is the red edges are +1, the blue edges are -1, yellow nodes are +1, and the black nodes are -1. Now look at the neuron over here. That one is currently a +1, but if you look at the total incoming field, the total incoming field is negative. So if you, as a result, the second neuron might just flip its sign and become negative. But because this neuron has become negative, it changes the field at other neurons. And now at this point, the figure becomes metaphorical because there's a bug in the figure. But you get, just to convey the idea, this is going to cause something else to flip, which may cause the original neuron to flip, and so on. Right? So overall, if the sign of the field at any neuron opposes its own sign, it's going to flip to match the field, which will change the field at other nodes, which may then flip, which may cause other neurons to flip, which may cause the original neuron to flip, and this can go on and on. Right? So here is a little illustration of the kind of behavior you can actually expect to see. So in this case, we have a loopy network with, I don't remember exactly how many, 24 neurons, I think, or 20 neurons. And you can, I'm just showing you 20 evolutions of this network. It started off at some point, some neuron flips, that causes another neuron to flip, which causes other neurons to flip, and you can see how the whole thing keeps flipping. Right? Now, here's a little longer animation of the same thing. This is 120 evolutions of a loopy network. Each neuron is trying to align itself to its own field. When it flips, it causes other neurons to flip, which cause other neurons to flip, which may cause the original one to flip. Right? How long? And at each point, all the what is happening is that every neuron which doesn't align with its current field tries to flip to align itself. So the question is, if I let this continue, is this going to continue forever? Right? Anybody want to take a guess? How long would such an evolution continue? Anyone of you there? So, is there a guarantee that there is an equilibrium? It turns out there is. And there's a very clean mathematical way of showing that this is not going to continue forever. But first, observe what happens, right? Consider any specific neuron. So let y minus be the output of the neuron before it responds to its current field, and y plus be the output of the neuron after it responds to its current field, assuming they're changing sequentially, right? So if the current output of the neuron matches the current sign of the current field, that's not going to flip. So that means that this difference, if I take the product of the field and the output, this product is going to be the same before it flips, before it considers the current field, and after it considers the current field, because there has been no action. It was already aligned with the current field, it's not going to flip, right? But then if the thing is if the current output y minus does not match the sign of the current field, that's going to flip. So if you take the product of the current output and the current field, which is y times the field, and you take the difference of this product after the neuron has responded to the field and before the neuron responded to the field. So if you take y times the field after it has responded minus y times the field before it has responded, if the field and the neuron do not align, then y plus is going to be different from y minus. Specifically, y plus is going to be minus of y minus because it has flipped, right? So this guy, I can simply write it as y plus minus y minus times the field, which is simply going to be 2 times y plus times the field, right? So that arithmetic is straightforward. Now, what else happened? When the neuron flipped, what did it do? It aligned itself to the field, right? So what is the sign? What is the sign of this guy? What would the sign of this one be? Anyone? It's going to be guaranteed positive, right? So in other words, this difference, every flip of a neuron is guaranteed to increase this value, right? The product of the output of the neuron and its field, right? At this point, can anybody tell me why it's not going to continue to evolve forever?
Because the weights and the biases are fixed, and there is a particular maximum value that you can reach for the flipping sign.
So this thing is bounded, right? Every term over here is bounded. It's just a linear affine combination of values. The weights are bounded, the biases are bounded. There's a maximum value that the field can take for a fixed set of weights and biases. So there's a maximum value that this whole there's a point beyond which this really cannot continue to increase. So to see what this means, consider this guy, right? Let me consider the sum of the product of the output and the field computed over all neurons. That is the d value, right? So this guy, I've just sort of expanded it out. I've pulled out the weights component and the bias component. And of course, there's no connection from a neuron to itself, so I haven't actually written it. There's a j not equal to I. If any neuron flips, it's going to result in a change in the d, right? So the change in the d is specifically the value of the d where you use the post-flip value for the neuron minus the value of the d where you use the pre-flip value of the neuron. And you know exactly what the difference, because you're only considering one specific neuron, you know the change in this d value after the neuron has responded, which is simply going to be 2 times y times field, right? And so what this means is that every flip of a neuron is going to increase this d. And the d is bounded. There's a point beyond which you cannot increase d, because every term that contributes to d is bounded. So as a result, it keeps increasing, but then once it hits the ceiling, it cannot increase anymore. Right? So this evolution is not going to be, it's not going to continue forever. At some point, it's just going to stop. Now, so flipping a unit will result in an increase, or at least a non-decrease of this d value, which is bounded. And it's bounded, of course, because the y's are either plus 1s or minus 1s. So the bound is simply going to be the sum of the magnitudes of the weights and the biases. And the smallest increment in d due to a flip of a neuron is going to be the smallest of these values, smallest of the field values, right? Meaning the field at any neuron is just this guy. Twice this field is going to be the change, and the smallest magnitude is the smallest change in delta, delta d. And so if every change, every flip results in a delta d change, and if if there's a maximum value for d, then the number of evolutions is just going to be upper bounded by d over the minimum change delta d, right? So you can't have more flips than that. It must eventually converge. So now again, this is a Hopfield net. This d value, we're going to give it a name, but we're going to not use the d value as this. We're going to take the negative of the d value, and I'm going to call it the energy of the network. And so the evolution of a Hopfield net keeps reducing the energy of the network all the time. And it's going to continue until the energy kind of plateaus. So the story so far is that a Hopfield net is a loopy binary network with symmetric connections. Every neuron attempts to align itself with the sign of the field at the neuron. Given an initial configuration, if I just set all the neurons to some initial configuration, the neurons will begin to flip, where each neuron tries to align itself with its field. And this is going to result in an evolution of the network, which will continue until the energy of the network itself cannot decrease any further. But the evolution is guaranteed to decrease the energy of the network. So now, everybody with me so far, right? Where did this notion of an energy come from? Why are we even talking in terms of energy? I could have been talking about, I could have given the thing any other name, right? It turns out all of this relates to a very physical phenomenon, which is spin glasses. There's a very nice book by Giorgio Parisi on spin glasses, which used to be very popular in the days in which Hopfield nets were first proposed. Now, a spin glass is a collection of magnetic dipoles in a disordered magnetic field. So every dipole is going to be having either a plus-minus orientation or a minus-plus orientation, north-south or south-north, right? And then every dipole is going to try to align itself to the local field. And if the dipole is not aligned to the local field, it's going to flip. But the field at every dipole also depends on the values of the other dipoles in the medium. And so when the dipole flips, it's going to change the field all around the medium, which is going to cause other dipoles to flip, which will cause a change in the original dipole, and so on. And so you can define the total field at the current dipole as simply a weighted sum of the values of the other the total field at any dipole is a weighted sum of the values of the dipoles of the other dipoles in the medium, plus the influence of an external magnetic field. So the influence of any dipole j at the current dipole I is going to be dependent on this coupling j, which is shown by the capital J, which is dependent on multiple things: the dielectric constant for the medium and the distance between the dipoles, and a bunch of other factors, right? So if I think of P as the vector position of the ith dipole, the field at any dipole is simply going to be a function of the vector position of the current dipole, and it's going to be the sum of the field contributions of all the other dipoles. Now the contribution of a dipole to the field at any point depends on its interaction J, and this whole thing is this whole model is derived from the Ising model for magnetic materials, which basically explains how these materials behave. So again, this behavior begins to look very familiar, right? If the current dipole is aligned to its field, it's not going to change. But if it's not aligned to its field, it's going to flip itself. It's just going to become minus of itself. So which again says that if the product of the current value of the dipole and the field is positive, the dipole will not change, otherwise it's going to flip itself. So a dipole flips if it's misaligned with the field at its location. And a flipped dipole changes the field at other dipoles, which will flip. The whole thing continues, exactly like the Ising model. When will it stop? Now the entire process while you can derive upper bounds on how many evolutions and such like from a purely mechanical perspective, there's actually physics behind it. You can define a total energy for any system. And in this particular case, it's an electromagnetic system. The total energy, the contribution of any single dipole to the total energy is simply going to be the product of the dipole and its current field. You've done this in your first physics class, right? So the total energy of the system is going to be minus of the product of every pair of dipoles times the interaction constant, plus the influence of the external field. The external field is going to be different at every dipole, so the contribution of the external field is going to be b times x, minus b times x. So this is the entire entire Hamiltonian of the system. You can think of it in some sense as a potential energy of the system. And now we know something about systems with potential energy. They keep trying to evolve to minimize the energy they actually contain, right? Pretty much every energy, you heat up a system, it's going to cool down to reduce its energy. You set a dielectric medium in some configuration, it's going to evolve to reduce its energy. And so every single flip of a dipole is going to change the energy. And it's going to keep continuing to change until the energy cannot go down any further. So now I can sort of visualize the state of the system as some current configuration of all of the dipoles. This is not a continuous valued state. If I have n dipoles, then I have 2 raised to n possible state values, right? But I'm sort of visualizing this as a line, just for illustrative purposes. And every state has a corresponding energy. And if you actually plot it out, the energy is going to be the energy of nearby states. I can sort of, if I visualize this in some n-dimensional space, the energy of nearby states, which just differ by 1 bit, is going to be very close. So you can think of the entire energy contour as having a shape of this kind. And the current shape, the current state of the system has some location on this contour. You can think of this as the ball over there sort of illustrates the current state of the system. And then once you start the system in any state, it's going to begin evolving. It's always evolving to reduce the energy of the system. And it's going to roll down this energy contour. And when will it stop? Right when it hits the bottom, right? When it cannot change any further. Now, here's something interesting, right? Suppose the system is initially at this valley, and then I perturb it so that the state changes. Some of the dipoles flip. The system is going to go up the valley to some other location. Then I let the system be. It's going to evolve. Where will it go back to? Right down the valley from where I perturbed it, right? So if the system starts off in a stable state, it actually remembers that state. If you perturb it from that state, it's going to return to this state. This kind of phenomenon is used popularly in physics of materials. You've heard of shape memory alloys and things like that. You put it in some stable state, you distort it, it's going to evolve back to the stable state. And that's how it actually remembers its shape, right? In this case, this is what happens with a dielectric also, with spin glasses. So we see the physics of it, But then let's go back to the computer version of it. Here's the Hopfield network. This energy E is very analogous to the potential energy of a spin glass. And the system will evolve until this energy hits a minimum. In fact, the equation looks very much the same, right? And so now typically this bias term, which I have included in the equation so far, it's something you won't normally consider an external field. But let me correct myself. You do consider an external field, but having this bias term is like having an extra neuron whose value is just pegged to 1, and B, it's just the weights of the connection of this neuron to all the other neurons, and this is one neuron whose value is not allowed to change. So once you think of it that way, you don't need to explicitly worry about this one extra neuron. So I'm in the equations that follow, I will sometimes have a bias and sometimes not, depending on what is more convenient. But the point is that it's always implicit, right? So let me use the bias-free version of the equations. This is analogous to the potential energy of a spin glass. If I start off the end system at some configuration, which is to say I set every neuron at some state value, and I let it evolve. The system is going to sort of evolve down that configuration till it hits a valley, and it will hit a local minimum, right? Now, in this equation, I've done something here. I haven't actually summed over all j not equal to I. I've summed only over j less than I. Basically, I've halved the first term to make it strictly analogous to the spin glass. But regardless of how I do it, it's just a scaling factor. This is going to be the energy term that's actually going to keep reducing as the system evolves, and the evolution will continue till this energy plateaus. So if I start off the network at some configuration, it's going to continue evolving till it hits this plateau, till it hits the value, right? This is a very interesting thing. This is what we will call a content. There's an instance of a content addressable memory. Has anybody heard of this term? How do you normally address something in memory? So let's say I have stored some data in memory, and I want to recall it. How do you actually go about recalling it? What is the standard procedure? That's easy, right?
The address, and then you find where it is.
You just pull up the address, and you go to the address location, and you recall whatever is in that address location. But in a content addressable memory, the situation is slightly different. You can think of each of these minima as a stored pattern, right? So in a content addressable memory, instead of having a location in memory that you use to recall the pattern, you will say, this is very much like what happens in your brain. You start off with some vague recollection of something, and then you sort of reconstruct the rest of whatever it is that you're trying to recall. So you can think of having a system that stores some patterns, but then if you initialize with the system with a partial value for this pattern or a distorted value for this pattern, it will sort of figure out what the pattern really was. So you're addressing the memory not by the location in the memory, but by the value. You start off with a corrupt or a partial recall of the value, and it's going to start from there, and it's going to recall the entire pattern. So over here, the values over here are going to be your stored patterns. These are the patterns that the system remembers. And then if you start off the system in one of those locations, one of the states which are in the bowl of the valley, it's going to evolve, and it's going to actually recall that pattern. So it's a content addressable memory. It's also called an associative memory. You sort of associate patterns with everything in the bowl. So what happens really is that if you start off the network at any configuration, it's going to begin evolving. You have this energy, the energy contour, which takes different values over the state space, and it's going to sort of evolve until it hits a valley. Those valleys are the patterns it remembers. And bowl around the valley is where it can actually start to be able to recall it. The network will evolve until it arrives at a local minimum in the energy contour. And so we've also shown that every change in the network is actually going to result in a decrease in the energy, or at least not in an increase in the energy. So the evolution is monotonic. It's sort of going to monotonically go down to the valley, and then it's going to stay there. At least the way we've defined it so far. Now, for threshold activations, this entire contour is only defined on a lattice, right? Every neuron is either a +1 or a -1. So if I have n neurons, the entire network can only take 2 raised to n possible states. And all of these 2 raised to n possible states are on the corners of a hypercube, where any two adjacent corners differ in only 1 bit. And there are n, it's an n-dimensional space. The hypercube is going to have 2 raised to n corners. So the patterns, the system actually operates on the corners of a hypercube. And for threshold activation functions, the system always lives only on the corners of the hypercube. But you can actually have different activations than the threshold. You can have something like a tanh, in which case the output is continuous valued. It can also take values within the hypercube. So for tanh activations, it will stay within the hypercube, right? Now, here's a little example of a function of this kind. Now, this network has only 2 neurons. So I can actually define this entire network on a 2-dimensional space, the energy contour of this network on a 2-dimensional space. And if I show you the equal level sets, the level sets for this energy contour, they are shown by the little ellipsoids. And so in this particular case, you can see how there are 2 minima for this, 2 local minima for this energy contour. And as you keep going up, if you start off, regardless of where you start, it's going to sort of eventually go down the bowl to one of these 2 local minima. So this network remembers 2 patterns. And so if you started off from that blue dot at the top left, it's going to sort of converge slowly, evolution by evolution, till it exactly arrives at one of these blue dots, and it's going to stay there. So the blue arc shows a typical trajectory for a tanh function. Now, there are 2 minima. Why is that? So before we continue there, right? Here is the energy function that I had on the top left. If I put all of my weights in one matrix, and if I represent all of the states of the neurons as one vector, then I can represent the whole thing as the reason I must point this out is it will matter. So if I have several neurons, I can put all of the outputs as one vector y. I can put the W0, W12, W13, W21, 0, W23. I can put all of these as a matrix W. And then in that case, summation I less than j, wij, yi, yj minus half can simply be written as y transpose wy minus half. Just the math, just the straight up formalism, right? So over here, if you look at the energy, that's what the energy looks like. That's your formula for the energy. So now going back to this problem, why is it symmetric? Why do I have 2 minima? There are 2 interesting questions over here. A, why do I have two minima? And B, why do I have 2 minima, right? There are 2 different questions. So let's answer the first question. Why do I have 2 minima?
Because the weights are the same and
So basically this is a quadratic, right? E equals minus half y transpose w y. This is a quadratic. If I wrote E equals minus half minus y transpose w minus y, is the energy going to change? No. So if y is a minimum, minus y must also be a minimum, right? So you have the number of, for every minimum there's a ghost minimum, which is the negative of the original minimum. That answers the first question. Why are there two minima in this case? But there's the second question, right? Why are there two minima? Does it make sense for this function to have two minima? It's a quadratic, right? What sort of a function is a quadratic? It's convex. How many minima will it have? One. So why does this have two?
That's a constrained optimization. It's constrained. At the optimization, you can't take any values.
It's not optimization in terms of. Maybe somebody else want to take a guess. Yash is halfway there. Why does it have two minima? Or why does it have more than one minimum?
We're not looking at the end of the goal. We are sort of cutting it because of the constraints. So there are two places.
So what happens is, that although, so if I think about this, a convex quadratic is going to have a level set of this kind, right, in two dimensions. But then I'm only allowed to live on the corners of a hypercube. The corners of a hypercube themselves are going to be these guys, right? So which means I can only take these values, number one. And number two, even amongst these values, I place the hypercube. The bowl is not a sphere. The bowl is not perfectly circular. The bowl is narrower in some directions and wider in some directions, a fact that will actually be essential. So what this means is that these guys, which are on the on the nth level set, have higher energy than these guys which are on the n minus 1th level set. Right? If I assume that this is the 0th level set. So these two terms, these two corners, have lower energy than these corners. So if I start off in one of these two corners, it's going to end up in the other two, one of the other two guys. Right? So in fact, as you increase the number of dimensions, you're going to find more and more of these local minima. But the presence of local minima is because of the fact that you're only allowed to live on the corners of a hypercube. It cannot be continuous valued. And whereas the bowl itself is a nice quadratic. So why symmetric? Because if y hat is a local minimum, yeah.
So another way to see isn't it that since we have y transpose y, that is like the square of the norm is the mod. So the mod essentially will give you two minima. Is that not?
It's still a quadratic. You only have one minimum. X squared. It doesn't matter, right? It's still quadratic. And why? Yeah. So basically, if any y hat is a local minimum, so is minus y hat, right? And here is an instance with 3 neuron network. You have 8 possible states. Of these 8 possible states, you have 2 stable states, which are the two red corners. If you start at any one of the others, it's actually going to evolve into one of these 2 red corners. So here's an example of a content addressable memory. You can see the original figure is the one to the left. Every pixel is black or white, so every pixel has a plus or minus 1 value. I can actually construct a Hopfield network which stores 1 neuron per pixel. And then if the network is initialized with the figure in the middle, in one case it's degraded, in the other case the image is partial, and you let it evolve, it's going to end up with the figures to the right. Okay. So here is another little example which somebody put it. So someone actually built this little demo where they try to store multiple patterns, and then if you initialize it with one of these some random pattern, it's going to evolve to one of these guys. So depending on where you initialize it, it's going to evolve to one of those three patterns. Right? Not only have they started out with something random, they've damaged it further, and it evolves, and it recalls the pattern. It's a very beautiful content addressable memory, right? Now, it can also evolve to the exact opposite, right? Now, there's an obvious question over here. I've given you a content addressable memory, something that actually addresses memory by content. But then, what is the next question? How do you store a particular pattern, right? What is the magic? How did you actually make it remember something useful? Now, before that, let's look at the computational algorithm for how the whole thing actually evolves. You'd initialize the network with some pattern, and then you'd iterate over all the neurons until convergence, where each neuron is going to be made to align with its local field. You can do this iteratively, one neuron at a time, or you can do the whole thing in bulk. So, and continue the process, and it doesn't really change. Now, here is the interesting thing. This guy can actually be viewed as an arbitrarily deep multi-layer perceptron. How would I do that? Anyone? So if I think of my current neurons as this, then I can think of the situation after one evolution of the neurons as this one where every neuron connects to everything except itself, and right, and so on. And then I can have the next layer and the next layer, and this can actually be viewed as a feed-forward process until the whole thing stops changing. Now, if I tell you this, does this give you any ideas about how you can actually learn to store neurons, store patterns? This is just a standard MLP, right? If I want to store memory, what am I presenting? Target memories, right? What do I want it to recall? Anything that's distorted by a distortion of the original memory. You can literally sort of train it by thinking of it as this very deep MLP where every layer is exactly the same as every other layer, right? And then standard backpropagation should in principle be able to give you the parameters of this network. Make sense? Right. But that's not how we'll actually see it. Everybody with me so far? Yeah. So the story so far, a Hopfield net is a loopy binary network with symmetric connections. Neurons try to align themselves to a local field. Given an initial configuration, the patterns of the neurons will evolve until the energy of the network achieves a local minimum. And the network acts as a content addressable memory. If you initialize it with a somewhat damaged version of the minimum pattern, it will evolve into that pattern, effectively recalling the correct pattern from a damaged or incomplete version. So the issues here are, how do you make the network store a specific set or a pattern? How many patterns can we store? And how do you retrieve the pattern, the patterns later? Now, while I'm going to be talking about this in terms of content addressable memory and so on, this actually also informs you something about networks in general. Because think about this loopy network is really just an infinitely deep network or an arbitrarily deep network where the depth of the network depends on the input with the extra caveat that every layer is exactly the same as every other layer. But in fact, much of the math that we're going to see for this guy, or that we have seen for this guy, holds even if I change the weights from layer to layer. You can work this out. And you're basically going to see that as it goes down, you're basically every neuron is aligning itself to its local field, which is going to cause a decrease in the energy of the entire output. And as it goes from beginning to end, eventually the energy sort of keeps decreasing through the network, which means the limitations that we state about how it can store stuff, what is the amount of damage that the input can have before for it to be able to recall, everything is going to remain even for these other networks. Everybody get that, right? There's nothing fundamentally different between this loopy network and and just an unrolled network, just a conventional unrolled network. And that's beautiful. Once you change your perspective a little bit, you begin understanding these things in a nicer way, right? So let's consider the simple business of how do I memorize a specific pattern? How do I teach the network to remember, say, this image? This is Chip and Dale, is it? Or is it from Looney Tunes? I don't remember. So I have an image with n pixels. If I want to remember an image with n pixels, I'm going to need n neurons. And every neuron is going to connect to every other neuron. It's a loopy network. I'm not thinking of it in an unrolled way, right? So there are n times n minus 1 over 2 neurons in all, because I'm considering symmetric weights. Now, here's what. Remember that a network that stores a pattern p also naturally stores minus p. So if I'm trying to store minus 1, 1, 1, 1, minus 1, 1, then it naturally also stores 1, minus 1, minus 1, 1, minus 1, simply because the whole thing is symmetric, right? So now a network, we said, can store multiple patterns. Every stable point is a stored pattern. So we could, in theory, design the network to store multiple patterns. We actually saw examples of this, where there was a network that was storing 3 different patterns, right? So remember that every stored pattern actually corresponds to 2 stored patterns. For every p, there's a minus p. So if you're storing p, you're also storing minus p, right? Now, so if I want to store a pattern, my job is to design a weights matrix such that the energy is a local minimum at that weight, at the target pattern. Now this means I have 2 requirements, that if the system is in the current pattern, if the system is one of these in these target patterns, then it should not feel the urge to flip any bit. So the pattern must be one, stable. Stable because once you set the net in that pattern, then every neuron is aligning itself with its local field, so it should not feel this, irresistible urge to flip. But the second thing is that you must also be stationary. What do I mean by stationary? That if I set it in the pattern and flip a bit, it must want to go back. So the stable, there are 2 different aspects to it. You can be stable without being stationary. You can't be stationary without being stable, right? One of them. So the minimum requirement that we're going to have is that these patterns are stable. So let's say I'm trying to store only one pattern. Then you want this behavior. You want the sign of the field at every neuron to be the same as the value of the neuron. So this is a actually no, stable. Stationary is where things don't change. Stable is where flipping one makes it come back, right? So you want the pattern to be stationary, and we will use Hebbian learning. So if I use Hebbian learning, I just say that if I have a single pattern, then every weight is simply going to be the product of the 2 neurons. And you can see why this works, right? So let's say I want to store 1, 1, just 1, 1. If this weight is minus 1, then the neurons are going to keep flipping all the time, right? On the other hand, so if this weight were minus 1, this guy is going to see a field of minus 1, so it's going to become minus 1. So if this is minus 1 and minus 1, it's going to, am I getting it right? I'm off. But anyway, we'll see. So if you actually think of each weight as simply the product of the two neurons on either side, this should give you, this should make your target pattern a stationary pattern. This is Hebbian learning, right? Standard Hebbian learning. We saw this many, many classes ago. And let's see why. So my weight wji is simply yji, right? So this means over here that if I'm looking at the field at any neuron, it's going to be the sum over all of the other neurons of the product of the weight wji times wi, right? Or wji times wj. But wji was simply yij, correct? So if I expand it out, where I've learned the weights according to the Hebbian rule, that's simply going to be the product of yj times yi times yj, which is yj squared times yi, summed over all of the other neurons. But then yj squared is just plus 1, because y is either a plus 1 or a minus 1. If I square it, it's always going to be a plus 1. So this simply becomes some constant times yi. And so when I multiply that, so which means that the field at the current neuron for every one of these neurons is simply a scaled version of the neuron value itself, where the scaling factor is positive because it's a sum of squares, which guarantees that the sign of the field at each neuron is exactly the same as the sign of the neuron itself. No neuron is going to flip, right? So simple Hebbian learning is going to give you a stationary pattern. So the pattern here is stationary, right? Now you can also show that this is the lowest possible energy for the network, because every weight is going to be plus or minus 1, right? So when you actually expand it out, if you look at the total energy of the network, which is which you get for when you arrange the weights according to the Hebbian rule, the total energy of the network is simply going to be minus 0.5 times the count of the number of weights in the network. That's literally the lower bound on the energy, which means not only is the pattern stable, stationary, it's also stable, right? So simple Hebbian learning is guaranteed to give you to memorize patterns, and this memorized pattern is going to be both stable and stationary, right? So the pattern is stable. Here, let me sort of illustrate this. I'm showing you the Carnot map version of a pattern. You remember Carnot maps from lecture 2, right? So I'm trying to store 1, 1. It's a 2-bit pattern. I construct a network using just 2 bits, 2 neurons, and observe what happens. 1, 1 is going to be the pattern I'm trying to store, but consequently, minus 1, minus 1. Actually, this is a 4-bit pattern. So this is 1, 1, minus 1, 1, 1. That's what I'm trying to store. And consequently, the pattern, which is also the exact negation of every bit, will also be stored. The figure to the right shows the energy of the network at each one of the configurations. And so you see that the yellow, the pattern that I'm trying to store, has the lowest energy, and the darker the pixels get, the blocks get, the higher the energy. And regardless of which block you start off from, you find that there are neighboring blocks which have lower energy, so which means it's going to keep flipping, right? Keep walking down this sequence of lower energy neighbors till it arrives at one of the 2 yellow blocks. So not only is the pattern stationary, it's also stable, but then there is the issue that you have no guarantee about which pattern you're going to end up in. You could end up in either the positive pattern or the negative pattern, right? So now let me try to store multiple patterns. When I'm trying to store multiple patterns, if I'm still using the Hebbian learning rule, then I would just sum this weight or average this weight over all of the patterns that I'm trying to store. So for any particular edge, I'm going to take the average of the product of the 2 neurons on either side over all of the patterns that I'm trying to store. So that's still your Hebbian learning rule, right? So here the superscript represents the specific pattern I'm trying to store. I'd be summing over all patterns, the product of the two neurons on either side, and rather than sum, I should really be taking an average, but the average scaling factor doesn't really matter. Now, if I use this version of the Hebbian rule, how many neurons, how many patterns can I store? So it turns out that with some assumptions, you can show that if a network has n neurons, you can store 0.15 n patterns, provided they are far enough from one another. What do I mean by far enough? If I'm trying to store two patterns which are neighboring, then clearly I can't, flipping one pattern, one bit into the other pattern is simply going to keep the other pattern. So these may be stationary, but they are not necessarily stable, right? So you want the patterns to be far enough from one another, but if they are far enough from one another, you should be able to store 15 up to 0.15 n recallable patterns with some probability. This with at least 96% probability, if I'm correct. So where did that number 0.15 n come from? That number comes from this little bit of math. So consider I'm trying to store k n-bit patterns, right? Then the Hebbian learning rule simply has the average of the products of the bits on either side over all of the patterns. So for any pattern to be stable, for every neuron, you want the product of the field at the current neuron and the current value of the neuron to be positive for every single neuron. Otherwise, it's not going to be stable, right? It's not going to be stationary. It's going to begin flipping. Now, this means if I just use the Hebbian learning rule for learning my weights, if I replace this Wij by the formula above, this is still the sum over all the neurons. This term over here is the actual learned weight between Wi and Wj, and I'm multiplying that by the current field at Wj, and this is going to be the total energy. This is going to be the total energy contribution of any particular neuron. You want this to be positive, right? Now let's sort of break this up. If I break it up, so that's the equation on top is still the same thing, the first one. In the second one, I've sort of broken it up into two, where I have where in order to analyze the recallability or the stationarity of the pth pattern, I've pulled out the contribution of the pth pattern to the weight and the rest of the patterns. So now I have two terms, the first guy, which is from the pth pattern, and the second guy, which is from all the remaining patterns. Now if I have only the first guy, we already know that every single pattern is stationary and stable, right? Because we just saw that we can actually store one pattern using the Hebbian rule. Where things can go bad is if the second guy actually interferes. And so that's what we'll call the crosstalk term. So the first term, you will notice, is always going to be +1, because yj squared is 1, yi squared is 1. The first term is the average of n instances of 1. So the first term is 1. For this to actually not be a stationary pattern, the second term must be less than -1, right? And you can sort of analyze under what conditions the second term is going to be less than -1. Okay? So a pattern will fail to be remembered if this crosstalk term is less than -1. Now, if you think of it in terms of random patterns, not structured guys, if I try to randomly generate patterns for the network to remember, in the real world, you're not really going to be trying to store random patterns. But if you think of yourself as trying to store random patterns, then the question you're asking is, what is the probability that this crosstalk term is going to be less than -1 for any randomly generated pattern? And you can work out the arithmetic you can find out that if you are trying to store a large enough number of neurons and a large enough number of patterns, then this random guy actually ends up having a roughly Gaussian distribution. And if you work your way through the arithmetic, and this is very straightforward arithmetic, because it's simply the product of simple binary values, right? And it's just this is just a Bernoulli random variable. If you work your way through the arithmetic, you're going to find that if you're randomly generating pattern, there's less than a 0.4% probability that you will generate a collection of patterns that will act as an effective destructive crosstalk for any given pattern. So there's a less than a 0.4% probability that stored patterns will not be stable if the number of patterns you're trying to store is less than 0.14n. If you're trying to store more than 0.14n patterns, then the crosstalk term, the probability that the crosstalk term will destroy your ability to remember the pattern begins growing, and pretty soon you almost certainly will not be able to remember any pattern. Right? Now this only holds for random patterns, not for carefully chosen patterns. Okay? But this is the kind of limit that you can come up with. And again, a 0.4% ability, failure and recall is a horrible thing if you stop and think about it. In the real world, that means 4 out of 1,000 data entries that you would try to recall are not going to be recallable, which is very bad, right? So, but anyway, so a network of n neurons trained by Hebbian learning can store up to 0.14n patterns with low probability of error, which is computed assuming that the probability that any particular bit takes the value 1 is 0.5. Now, this happens if the patterns are far apart, right? If the patterns they're random, and one of the nice things about choosing random patterns is that typically they're going to be far apart. The best case of two patterns that are very far apart is that if they're orthogonal to one another. To shed some insight into what is actually stored, let's see some examples. Here again is the energy contour when we were just trying to store one 4-bit pattern, right? Now if I'm trying to store more than one 4-bit pattern, what I would like to do, remember that if you go back, we are trying to store, the patterns we store will be on the corners of a hypercube, right? So the patterns we store are going to be on the corners of a hypercube. And if you store this pattern, any pattern that's diagonally across is also going to be stored simply because it's symmetric. So what other patterns would you want to store? You want the other pattern to be as far away from both this guy and this guy as possible, because that's when you give it maximum room to be flipping bits and not getting lost into the other pattern. Two patterns are maximally far apart if they differ in how many bits? N bits?
But over here n by 2.
N over 2, because it's symmetric, right? So which means if two patterns differ in n over 2 bits, what does it mean? What is their inner product going to be if every bit is +1 or -1? If you take their product for n over 2 of the bits, the product is going to be +1. For n over 2 of the bits, the product is going to be -1. The sum is 0. Right? The patterns are orthogonal. So the farthest patterns are going to be orthogonal. Make sense to you guys, right? So if you have if the number of bits you have is not even, if it's odd, then if you can write it as 2 raised to m times L, then you're going to have at most 2 raised to m orthogonal binary patterns, simply because you don't have n over 2 bits to cancel each other out beyond that, right? So now if I'm trying to store two orthogonal 4-bit patterns, here is the energy contour that you're going to get. Now remember, this is a toroid. The two edges touch each other. The whole thing is a donut, right? So the two patterns that I'm trying to store are shown to the left. The figure to the right shows the energy contour. You find that the patterns I'm trying to store are stationary. And on the other hand, if I actually flip one bit and I let it evolve, where it's actually going to end up in is not clear at all. There's a 50-50 probability that's going to end up in one pattern or the other, right? Or it's ghost. So that's what happens when you have orthogonal patterns. So here's the crazy bit. If I have non-orthogonal patterns, here's the pattern I get. And in this case, the evolution is much clearer, right? There is a definite notion of what is closer and what is not. So although the math, the intuition tells you that if the patterns are all maximally distant, they're going to be more recallable. We found that when they're maximally distant, they're going to be confusable. Whereas if they're not maximally distant, if they're not orthogonal, then some patterns are going to be more recallable than others, but that's a good thing. At least something will be remembered definitively, right? So here I am trying to store 3 orthogonal patterns. 3 and this is a 4-dimensional space. And once again, you're going to see that all patterns are local minima. Now everything has been learned using the Hebbian rule. The weights are learned using the Hebbian rule. The patterns are all local minima, but then if you perturb any pattern by 1 bit, you have no idea where it's going to go. So the recall is random, right? But if I store 3 non-orthogonal patterns, I have at least one pattern which is going to be exactly remembered, which is the guy in the middle. It's stable for at least one flip, right? So you get this very interesting phenomenon where the patterns, in fact, the two patterns at the corners are not actually remembered, because if you are not actually stable, because if you flip a bit, it's going to go back to the pattern in the middle, which is stable. But at least when I try to remember 3 non-orthogonal patterns, I do end up remembering at least one pattern, right? If I try to store 4 orthogonal patterns, basically I don't remember anything. Now, can you tell me why this would be the case? Anyone?
There will be 8 boxes of same energy, and every neighbor will have. So from every neighbor, you could go to either 4 of them. Because
Every pattern, every box is stationary over here, right? So there's going to be no evolution. We will see why in the next class. It has to do with the fact that when I have 4 orthogonal patterns, any vector in the space can be expressed as a weighted combination of these 4 patterns, right? The evolution, what is the actual nature of the evolution? If my current set of patterns is y, if my current pattern is y, this is going to go to sine of w times y, correct? That is the evolution that we've got. Now, if my current pattern is 8, I can write any pattern. If I have 4 orthogonal patterns, I can write any pattern as this combination, right? And now, if I write w times this, then this is simply going to be a times wy1 plus a2 times wy2, and so on. And with the Hebbian learning rule, it's fairly straightforward to show that it's fairly straightforward to show that these stored patterns are just eigenvectors of your weights matrix, which means wy is going to be the same as y itself, which is the same as this guy, regardless of the pattern you're trying to store. It's going to be stationary. Trying to recall. So although the 4 patterns you're trying to store will be stationary, so will everything else be. So it actually is not a happy solution. If I'm trying to store 4 non-orthogonal patterns, though, I still end up with at least one stable pattern. Okay. So what I find is that Hopfield claims for a network of n neurons, you can store up to 0.14 n patterns, provided they are random. And we actually find that the actual number of patterns that I can store in some cases is actually significantly more than 0.414n. In 4 dimensions, 0.14n tells you can't even store one pattern, right? But we're able to store 2. So there seems to be n equals 4 may not be a good case for the actual for n equals I mean this is a fuzzy statement. You may be able to store more than 0.14n patterns, but maybe visualizing this with just 4 bits is not a great thing. So let's try looking at it with something bigger. If I look at 6-bit patterns, right, then for 6-bit patterns, if I try to store one pattern using the Hebbian rule, there's the energy map to the right, and you can see that the one pattern is both stationary and stable. But then you get these interesting things. You see this box in the middle, this little blue box in the middle. That little blue box in the middle is stable, right? It's a local minimum and it's stable. That's a memory that you didn't actually train the network to have. So that's what we'll call a spurious memory. And this is something that you happen to have all the time, even in your brain, right? You get spurious memories. So Hopfield originally sort of proposed this model as a model for the biological workings of human memory. And you can see that at least some of the phenomena that you see are analogous to what we actually encounter. If I try to store 2 orthogonal 6-bit patterns, then there's the energy contour. And now this is a 6-bit Carnot map, which means it's not a toroid. It's actually, there are many edges. Each of those 4 boxes is locally a torus, and those toruses have their own neighborhoods. So this visualization is not to be just taken as is, but you will still see that the patterns are stable and stationary. But if you look at the light blue regions, those light blue regions are also stationary, and they are somewhat stable. If you start off in a box adjacent to the light blue, you're going to end up in the light blue, and after that there's no reason for you to actually evolve, because all the adjacent boxes are either the same energy or less or more. So you have, once again, spurious fuzzy memories, right? If I try to store non-orthogonal patterns, things become a little bit clearer. I cannot have more than 2 orthogonal patterns in 6 bits, but I can have 3 non-orthogonal patterns. And once again, you're actually going to see in this particular case that if you look at it carefully, every one of these 3 patterns is not only stable, it's actually stationary. And or not only stationary, but it's also stable. And clearly, k over here is greater than 0.14n, right? And 3 is much greater than 0.14 times 6. The cost I pay is that I have fake memories, some things that are memories that really shouldn't be. But that's okay. Now, what made this work? Now, why was I actually able to store more than 3 patterns in this particular example? It has to do with the fact that these were not randomly generated. The entire analysis talks about randomly generated patterns and probabilities. But if I'm careful about how I design my patterns, I can always store more than 0.14 patterns, right? Which is not the same as saying that if I given a set of patterns, I can always find weights for those patterns. What I did was I said I generated patterns and then sort of optimized the patterns and the weights so that they could be remembered in this particular example. And I can go up to 4 non-orthogonal patterns, and here you find that you have even fewer. Here's the interesting phenomenon. As I increase the number of memories, the number of bogus memories actually seems to be going down, right? So the behavior is kind of not very intuitive in that sense. You would expect that as you try to remember more and more, you are more capable of remembering rubbish. But that doesn't seem to be happening there. And then in this particular example, when I try to store 6 patterns, the whole thing kind of breaks down. I'm not able to do so. But multiple patterns are still stationary and often stable, meaning I'm always able to store more than 0.14n patterns. And I can keep doing this. I have more examples over here with 8 bits. And with 8 bits, you can actually find that I can store 3, 4, or 5 stationary patterns. So here is the overall observation. There are many parasitic patterns, undesired patterns that also become stationary or stable basically attractors, which are fake memories, things you are not trying to remember that you can actually remember. But there's also this business that there's the apparent capacity to store more than 0.14 n patterns. Right? Now, where do these parasitic fake memories come from? The parasitic fake memories come because the sums of odd numbers of stored patterns are also stable if you're using the Hebbian learning rule. I will leave the proof for this to you. It's trivial. But I can see very simply that if I've learned to remember YA, and YA becomes stable and stationary, and if I've learned to remember YB, and if I've learned to remember YC, then YA plus YB plus YC also ends up becoming a memory. If I'm using the Hebbian learning rule, where the Hebbian learning rule says that every weight is simply the average of the products of the neurons on either sides, where the average is taken over all the patterns you're trying to store. Now this means that if you look at the energy contour, you're going to get these little dips at every location, which is the sum of odd numbers of valid patterns. And as a result, you're going to get all of these fake memories. Right? So the capacity of the network, we see, it seems to be capable of storing more than 0.14 n patterns. And it's possible to make more than 0.14 n patterns at least 1 bit stable. Patterns that are non-orthogonal, strangely enough, seem to be easier to remember than patterns that are maximally distant from one another, for a very crazy reason, that once they become orthogonal, they actually end up becoming eigenvectors of your weights matrix for Hebbian learning and for Hebbian learning alone. Right? So the question is, can I actually sort of do something better? Is there a better way of designing the weights matrix for my network so that I have greater control over what I remember and how much I remember, and what are the limit, and improving the limits on the number of patterns I remember from 0.14 n. Right? So the story so far is this. A Hopfield network is a loopy binary network with symmetric connections. Given an initial configuration, the patterns in the neurons will evolve until the energy of the network achieves a local minimum. But the network must be designed to store your target memories. And this can be trained by Hebbian learning. But if you use Hebbian learning to store your memories, then you can store for any n-bit network with a probability of less than 0.4% of damage, you can store a max of just 0.14 n patterns. Right? Although empirically it appears that you might actually be able to store more patterns than that. So here I'm going to make a bold claim. I will say that I can always store up to n orthogonal patterns such that they are stationary. In an n-bit network, I can always store up to n orthogonal patterns. And so in the next class, and I can also avoid spurious memories by adding some noise during recall. Okay? In the next class, we're going to see how, and we are also going to see how, if I want to store n-bit patterns, I can still go ahead and store more than n-bit patterns. Although the inherent limitation in a Hopfield network is that I cannot store more than n patterns. And the reason I cannot store more than n patterns is that once I've stored n patterns, as you can see from this little example, those n patterns basically span the space. After that, you have linear dependencies, which means the patterns cannot really be recalled. But we will nevertheless see how you can store more than n patterns. Right? So I'll stop right here, and we will continue in the next class. I'm not entirely sure why I have this picture, but I think it's because it says to be continued.